Hello, my dear NEET warriors. I hope I'm audible and visible to all of you. Hello, Krishna, all the warrior Pandus. Hi, Sukanya. Hello, Madhumati. Good evening. I hope you guys are all ready, excited for the next session by your very own Captain Shreyas Sir in the NCERT line by line series. Guys, we are going to complete 3 chapters, today, and after this, we'll move on to the 4th chapter. So, guys, you should really be, subscribed on the channel so that you do not miss any of the classes. And within no time, just, with the flow, you will complete the entire NCERT. You not only it will be useful for your NEET exam, but also students who are preparing for different board exams, right? So let's go. Quickly mark your attendance, show your support for the only NCERT line by line series in English on YouTube for absolutely free of cost. Show your massive support and let your friends know as well. It's not just liking, you should let your friends know in the school, in your college, right? So today we're going to do the part 2 of this. Part 1 was already done just few days back on the channel. Like you can see over here, this was part number 1. So today we are going to do basically part 2. And those of you who have forgotten to register for MVSAT, please register right now. Time is running out and you will forget because the test is near. I want you to start preparing. When you register, it sticks in your head. Test is coming. I have to prepare. Don't worry, even if you have not completed the full syllabus, it will tell you where you stand. Online is there between 10 to 20 October and offline starts 29th September in your nearest Vedantu Learning Center. Because I want you to, get those free study material by attempting whatever, goodies you get. It will be definitely useful for your NEET preparation. And who knows, you might win some scholarship or maybe some prizes. Never think low of yourself. I'm pretty sure you warriors, you lions are going to do well. Correct? So let's begin with the class. My dear students, hi Atluru, nice to see you back. All the warrior Pandus, hi Dr. Yashvi, Nixon, Disha, hi Satyashri, hello Jasmine. Good evening, my dear warriors. So last lecture we have completed in part 1 what is current, how to find current when charge is changing by differentiating it. We have seen the theory of current on with the example of houses, Pandus and Champa. We have also seen Ohm's law and how to find the resistance being rho L by A, right? Then electric field is J rho, these concepts. We have also seen drift velocity calculations. All of this was done last lecture. Even conductivity formula and all the numericals which were there. Mobility is done. Limitations of Ohm's law, resistivity of different materials. All of this was done in the last lecture. Now, time for lecture number 2. I have written down right over here. So, section 3.9. Ready for it? Okay. Let's go. So, yep. Starting off with electrical energy and power. Consider a conductor with certain endpoints. I will read it for you. Some important things will underline and I will obviously explain it to you. So imagine it is moving from one point to the other. Current I is there. At some point A and B, the potential is VA and VB. Since the current is going from A to B, always current goes from high to low voltage. So that's why VA is more than VB. And assume that the voltage difference between them is V. If some charge goes in time delta t, then the potential energy at that A by definition will be charged into voltage and at B will be charged into voltage. So the change in energy will be a charge into potential difference. But charge flown is I delta t. So then they say that the charge moved without collision through the conductor, their kinetic energy would also change the total energy. Conservation of total energy would imply that this, hence this, and then they say thus in the case charges are moving freely under the action of electric field, kinetic energy would increase. However, we see average the charge carriers do not move with acceleration but with a steady thing. Okay, 1 second. Let's underline important things. This is the voltage difference. The charge flown is basically I delta t. Okay, so if the charge moved through the conductor without collisions through the conductor, their kinetic energy would also change so that their total energy is unchanged. But this is very important. However, seen earlier, charge carriers do not move with acceleration but with a steady drift velocity. This is because of the collisions with the ions and the atoms during the transit. And this energy gained by the charges is shared with the atoms vibrate vigorously, conductor heats up, thus an actual conductor, the amount of, very important, thus in an actual conductor, an amount of energy dissipated as heat in the conductor during the time interval is given by this, and that's how they get this formula. P is equal to voltage into current, which you can also write using Ohm's law as this. Okay, now what do they really mean by this particular thing? See, I'll explain this to you. Remember, inside a conductor, imagine this is a conductor. It is the electrons which basically move. It is the electrons which basically move. And that movement happens because of the electric field. That motion of the electrons because of electric field inside of it. And we have seen that because of the electric field applying of force, ideally it should have accelerated with the force divided by mass, which means the velocity should have increased continuously, but it doesn't happen like that. Why doesn't it happen like that? Because these electrons don't just go in a straight line continuously, rather they continuously, collide with different atoms, other electrons here and there. So because of collisions, what happens is there is acceleration for some time, then they lose the velocity during the collision, and again repeat the process. Therefore they end up moving in an average manner. They move in an average velocity, which is basically called as your drift velocity. Everybody agrees with this? Everybody remembers this logic? Yep. Increase the volume, just 1 second. Is the volume less, guys? Hello, just check it now. Is it fine? Guys, now? Just check it out. Is it fine? Is the volume fine, everyone? Let me know. Just give me a thumbs up. Yeah, now it is fine. All right, pakka. Cool. All right, just refresh in case of connectivity issues. Okay, right. Okay, so I had explained before that the electrons end up moving with an average velocity called as the drift velocity. So imagine there is a conductor, and if there were no collisions, then what would happen? That particular electron, the charge carrier, would continuously accelerate, and it would increase its kinetic energy. If kinetic energy is increasing, some other form of energy should decrease. So basically the potential energy will decrease. So the potential energy basically got converted into kinetic energy. But we know the velocity does not continuously increase, rather it maintains a steady speed, which means all the potential energy that it gains doesn't go in this path, it doesn't go in the kinetic energy, it basically is ending up lost. It is ending up as a loss of energy, it is lost as heat. It is lost as heat. So this is exactly what happens. So whatever potential energy it loses, ideally it should get converted into increase of the speed. But even before it reaches very high speed, what happens? It ends up colliding. So it loses in the collision, and when it collides, what happens? The molecules begin to vibrate, and these vibrations only are nothing but thermal energy. What do you mean by when something is hot? When something is hot at the molecular level, the molecules are vibrating more vigorously. They are rotating, twisting, moving here and there. So when there is more randomness, more energy, then thermal energy, basically temperature is more. If it has less heat, less temperature, the molecules are pretty much, chilled out. They are not moving so much, very less vibrations. So hence it is said that the loss of the potential energy is going as heat. Is that absolutely clear? So in order to find how much heat is lost as conductor, lost as heat during collisions, so basically this particular heat loss per unit time is called as the power loss in the conductor. This is called as the power loss inside that particular conductor. Okay, I hope till this point everybody is clear why power loss happens in a conductor. You pass a current in any wire, any conductor, any resistor, any device, there is always some power loss. Well, it depends on the current and the resistance, but yes, why it happens, you should understand that. Okay, now in order to find that out, in order to find how much is that power loss, what they have done, they have found out how much heat is developed per unit time. That heat is basically the difference of the electrical potential energy. Electrical potential energy. Now, electrical potential energy difference is the charge which flows, into the potential difference itself. If you remember, this was there in electricity, electrostatics. Delta U is Q delta V. Okay. How much charge will flow? Charge is nothing but current multiplied by the time. And this is nothing but delta V divided by delta T. Delta T cancels, so it will become I delta V. But usually we do not write the voltage difference as delta V. Sometimes we end up writing it as just V. This V is just saying potential difference, basically delta V. So that's how you get power is equal to current into voltage. Now this same derivation they have done over here, but NCERT loves to confuse students. They get pleasure. So every time a student get confused, they get 5 brownie points. They become very happy. Yes, we confused 10,000 students today. Okay, I don't know, maybe they derive some pleasure. So the way they have explained it, fine, it's good for teachers, I understand it. But Pavam kids, yeah, I mean, just imagine Pavam Pandus and Pachampas. It should be simple. It should be something like, any book should be something like which even a 6th standard student should understand, should develop interest. But that's why I am here. Your captain Shreyas Sir is here, who is going to help you out and decode NCERT for all of you. So I have explained this to you in a beautiful manner. But we also know that, voltage, this voltage is nothing but current into resistance. So therefore, I can also write P is equal to I into I is nothing but I squared into R. We can do one more thing. Current, we can also do one more thing. Current is nothing but voltage by R. So therefore, power can be written down as V by R into V. Therefore, power is equal to V squared by R. How did I get it? Using Ohm's law. So this is also correct. There is nothing wrong in this. This is also correct. Nothing wrong in this. This is also correct. Which one will you use? Depends. What is given? Voltage and resistance is given, you will use this. Current and resistance is given, you will use this. Current and voltage is given, you will use this. If they tell voltage is changing, resistance is constant, voltage is changing, resistance is constant, something you have to find, you will use this. Current is constant, resistance is changing, you will use this. Current is changing, voltage is constant, you will use this because it has current and voltage. Depending on which terms are being used, accordingly you will use one of these formulas. Okay, so that's what they have basically done till here. So that is the energy lost at per unit time. Where does this power come from, you might ask? So this power basically comes from some external source. So they have mentioned where does this power come from. The power comes from external source to keep a steady current through the conductor. Do you remember that Pandu Champa example of houses which I gave you guys last lecture in part 1? Where is it? Oh my god, yes, here. These houses are like the nucleus, the Pandus were like the electrons and some Champas came. So if one Champa comes, the Pandus run out of the house to meet the Champa. Those Pandus were like the free electrons of the conductor. The conductor is okay to let these Pandus leave that house. So that's why it's a conductor. Insulator won't leave these electrons, it will hold them inside that house, the house being the atom. Okay, now if there is a constant supply of Champas, Pandus will keep running out of their houses. So that's how you maintain that current. So you need to supply Champas, meaning you need to supply an external agent. In this case, you need basically nothing but a battery. So remember, my dear warriors, you need something like this. So these batteries, right? These batteries. So these batteries are exactly like these Champas. These batteries are like these Champas. Without this battery, these Pandus wouldn't have left their houses. The conduction of electricity wouldn't have even started. Yes. Is that right? Correct? So that is what they say. Okay. Yes, that's why Krishna is a very ideal, best student. I'm pretty sure Krishna enjoys the classes, and I wish we had a lot of more Krishnas too. Thank you so much, Krishna, being such a wonderful and lovely student. Isn't it? Okay, so that is what they have mentioned. And you know, this energy of heat loss basically comes from the energy stored inside this cell. Inside the cell, what is happening? Some chemical reaction is happening. You connect some wire, some chemical reaction is happening. So basically, it should come from chemical energy. So it is the chemical energy of the cell which supplies this power for as long as it can. That's what they have explained. Okay. Now, electrical power they have told blah blah blah. Okay. Then, yes, in the connection wires from the power station has a finite resistance. The power dissipated in the connecting wires, which is I squared R. Just to derive the power, the wasted power in connecting wires is inversely proportional to V square. The transmission cables from the power stations are basically hundreds of miles, hence RC is considerable. To reduce this, basically you are going to use large values of V, and that is why you will see that okay, transmission lines are away from the populated areas. Using electricity is not safe. Okay, device called as transformers is used. Okay, now I'll tell you what happens. See, imagine you go to a waterfall. Water falls on a turbine. Water falls on a turbine and it starts rotating the turbine. What kind of energy does the water have? It will have gravitational potential energy. When it falls on the turbine, it basically rotates it. So it will give it rotational kinetic energy. That rotational kinetic energy is then converted into which kind of energy? It is connected to a generator, so it is converted into electrical. It is basically converted into electrical energy. Is that okay, everyone? So if water is continuously falling on a turbine, okay, at a power plant, at a generator, you will see continuously rotational energy is being created and continuously energy has been supplied in electrical form. So that's how you get a power from the generator or from the power stations. It could be thermal power plant, nuclear power plant. This is a hydro power plant. Fair enough. Now imagine this power has to travel a really long distance. It has to travel a really long distance. What will happen because of that? The resistance of such a long wire, because it is directly proportional to the length, will be more, because it has to travel from one city to the other. The power plant is somewhere in some state, your house is somewhere else. So because the length is more, the resistance will be more. Do you guys agree with it? Do you guys agree with it? Now, inside this wire, obviously there is some current flowing. So what is the power loss in that particular wire going to be? The power loss in that wire will be current flowing in the wire into resistance of that particular wire. Everybody agrees with this? Into resistance of that particular wire. So if the wire is long, resistance is long, then the power loss will be more. So normal person will think, sir, I will reduce the resistance, I will use a very good material. I'm like, sir, which material do I use? Sir, copper. Even if you use copper for such long distances, the resistance is huge, because we are not talking about 1 or 2 kilometers, couple of hundreds of kilometers. So definitely it will increase the resistance. So can I use silver and gold? If you use silver and gold, people will steal those wires and go off. So you can't use silver and gold, and even if you use silver and gold, still the length is too high to increase the resistance. So you can't do anything with the wire resistance. The only thing you can play around is with this current. So if you reduce this current, since it is being squared, so if the current reduces by half, I square will reduce by 1/4, power will reduce by 1/4. If I reduce the current to 1/10, I squared will reduce to 100th, I will save the power by 100th, guys. So hence the power loss will also decrease. So my aim is always to reduce the current flowing in it. So what they do is there is some kind of a device which we will study later on, which basically is called as a transformer. Autobots assemble. Not that transformer. Yes. So that transformer, what it does is it increases the voltage, thereby reducing the current. So because the current reduces, that's why you will see the power reduces. Like, sir, if the voltage is so high, then how will it come to our house? Don't worry. On the other side, there is another transformer which again reduces the voltage and increases the current back to its normal value. Before it is supplied to your house. That's what they do. Whatever they do here, they do the exact reverse before it reaches your house. Now, since this current is very low but the voltage is high, this is high voltage line. What is this? This is high voltage line. So generally it is not advisable to stay near a high voltage line. So that's why you do not build any houses, etc. near such lines. That is what they have explained. Okay, that is what they have explained. So blah blah blah, the transmission long distance transfer, but it is, so I'll just mention it over here. To reduce the power loss, these wires carrying current at enormous values of voltage and this is the reason for the high voltages danger signs on the transmission lines. Okay, as simple as that. So this is what they have explained about power loss and how it can be reduced for long distance transmission. Understood? Very good. Excellent. Now let's move ahead to the next concept of cells and batteries and all these things. Okay, so they have given some concepts over here. So let's understand over here. What is a cell? Cell is basically a device which maintains steady current. A simple device to maintain steady current in a circuit is a cell. It has two electrodes, one is positive and obviously one is negative. So there are some electrolytic reactions which happen and through which you develop a potential difference. The difference of that voltages between the positive and the negative terminal is called as EMF or the electromotive force. So it is the difference of those voltages on the positive and the negative side. So that is your EMF of the cell. EMF is actually potential difference, very, very important, and not a force. Although the name suggests electromotive force, the unit is not Newton, it is in volts. People earlier thought that batteries give force, but actually batteries do not give force. It is going to give voltage difference. But since the name had already been given, it was too late, so they continued with it. Just like you might have heard, somebody in their childhood was just called Chiku. Now Chiku, that name became so common that the actual name, maybe it was some Rohit, okay, or Sham or Roshan or Rahul. People forgot the original name only. And since we have been calling him Chiku, so we continue calling that person as Chiku. Same way, actually, EMF, the name was given earlier, but people realized it later, but it was too late. So they continued calling it EMF, or else it should have been electromotive voltage. Cool? All right, everyone, till this point? Okay, so this is used because of historical reasons. That's all. Now, EMF is actually potential difference, not a force. See again, what is this NCERT doing? Okay. To understand the significance, consider a resistor. Okay, as explained before, steady current is maintained because of the current which flows clearly across the electrolyte. The same current flows through the electrolyte, whereas P2N, the electrolyte through which blah 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 finite resistance is internal resistance. Okay, this is again an important point. The electrolyte through which the current flows has a finite resistance R, which is called as the internal resistance. Where potential difference between P and N, now V is potential difference between P and A, potential difference between A and N, blah blah blah. Thus, EMF is the potential difference between the positive and negative electrodes in the open circuit. EMF is the potential difference between the positive and the negative electrodes in an open circuit. That is when no current is flowing through the cell. If, however, resistance is finite, current is not zero. In that case, potential difference between P and N is this. Okay. However, okay, R is finite, is not zero. However, if R is finite, current is not zero, the potential difference is given by V is equal to E minus IR. Okay, fair enough. For practical calculations, internal resistance in the circuit may be neglected when the current is such that it is very, very small. The EMF is very large and IR is very small. The actual values vary from cell to cell. Internal resistance of dry cell, however, is much higher than the electrolytic cell. Okay, another important line over here. The internal resistance of dry cell, it can come as a statement based question, is more than an electrolytic cell. Okay. Now, let me explain this all to you. Don't worry. We also observe, since the voltage difference is blah 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 from Ohm's law, combining the equations, current is E by R plus R, the maximum current that can be drawn. Okay, this is another important point. The maximum current that can be drawn is for R is equal to 0, and this is basically E by R. Okay, perfect. However, in most of the cells, the maximum allowed current is much lower than this to prevent permanent damage to the cell. Okay, let's understand what this means. Let's understand all these paragraphs, whatever I have written. I have first of all highlighted the important things. Okay, I have first of all highlighted the important things. So the negative electrode develops negative voltage, the positive electrode develops the positive voltage, and all of that. See, when you take a battery like this, this is your positive terminal, this is your negative terminal. For example, the positive terminal developed plus 3 volts, the negative terminal developed minus 4 volts. Then what would be the voltage difference between these two terminals? What would be the voltage difference between these two terminals? Okay, think and tell me. I am very good, Rakshana. Hi Rakshana, thank you so much. Why does it show DNA below? To remind you, if you are not yet a part of DNA batch, be a part of it. DNA students are already active here also and there also and already ahead. So if you are not yet aware of the DNA batch, be a part of it. It's just to make you remind you of that. Okay. So what do you think, guys? What's the voltage difference going to be? Is it 1 volts, minus 1 volt, 7 volts, minus 7 volts? Think about it. I don't think it is minus 1. The voltage difference will be this minus this. So 3 minus minus 4. So it will be basically 7 volts. 7 volts. This voltage difference is basically your EMF of the cell. So the EMF of the cell is basically the positive voltage minus the negative voltage. But if the negative voltage is already written down in the negative sign, so this will become plus. Understand that. Or else you can just think of it as V plus plus V minus modulus. This was 3, this was 4, 3 plus 4 is basically 7. So that becomes your EMF. Is this part understood? Is this much part understood? The voltage difference between the terminals of a cell is basically the EMF. But when do you measure these voltages? When there is no current flowing through this. When out of this the current should be 0. Nothing should come in, nothing should go out. Such a circuit, when there is no current, it is basically called as a open circuit. What is it called? As an open circuit. It is not closed, it is open. Okay. To represent it, I will just show it like this. A battery with some resistance inside and nothing is connected, it's just open. So then the voltage difference between them will be the EMF. Alright, the voltage difference between them will be the EMF. This is called as a open circuit. Right now, these batteries which are sealed inside, do you think they are open or closed? These batteries which are sealed inside, come on, put it up in the chat box. Is it open circuit or closed circuit? Are they connected by wires to anything back? Is there current flowing? Definitely not. Is it consuming the energy stored inside it? Definitely not. So that's why right now all these batteries are in their open circuit form. Yes. Sukanya, I taught resistance in the previous lecture, part 1. Please check that out. Please check that out. Okay. Great. Now, what is this internal resistance? Basically, inside this battery, when the current flows, inside this battery, when this same current would have flown, you will encounter some resistance because of that chemicals or those electrolytes or that dry powder which is there. So that resistance is basically called as the resistance inside the cell. That is why internal resistance. So through the battery when they go, they encounter a resistance that is shown as internal resistance. You can show it here or here outside the cell, that's okay. I know it is inside, but you can show it outside. There is no harm. But all of this happens inside. There is EMF and there is some loss in that internal resistance. Now, the reason why we told it should be an open circuit to measure the EMF, can you tell me why? The reason is, if current was going, don't you agree there will be some loss in voltage across the resistance? If current was not zero, I squared into R will cause some energy loss, will also cause some voltage loss across this. So this voltage will not give me EMF. Hence, to measure the actual EMF, make sure there is no or negligible current going, then that voltage gives me the EMF. Negligible current means no difference in the voltage across this. That's why I will get the true EMF. Otherwise, it will be different. Now, imagine I use these batteries inside a toy train or inside a torch or inside something. Okay? Do you think the voltage difference across those terminals, which was earlier, let's say 7 volts, will it remain 7 or will it increase or will it decrease? When I'm using this battery in a circuit, it is lighting up a bulb, it is turning on a motor, it is doing something, it is heating something. Do you think this difference, will it still be 7 volts or will it be less than 7 volts or will it be more than 7 volts? Put it up in the chat box. Yes, it will be obviously less than 7 volts. Why will it be less than 7 volts? Because the moment you have this cell and you find that there is some current which is going in it, you will quickly see that this particular voltage difference between them will no longer be E, it will be E minus IR. Why minus IR? Because there is a drop in the voltage. Instead of E, some voltage is basically drop in the potential across the internal resistance. That's the reason for this. So V will be equal to E minus IR. I hope this is absolutely clear for everyone. Everybody with me on this? Clearo? One such example for that will be, imagine I take this battery, connect it to a resistance and it is passing through some device. It is passing through some basically device. Usually a device is also called as a load. You are loading the cell means you are connecting it to something. So there is some current. So in such a case, when the current is going in this circuit, if I use Ohm's law, then that current will be that voltage divided by the total resistance. In this case, the voltage is nothing but E. The resistance is R plus R. R plus R is the total resistance. So that would be the current flowing in that particular circuit. And when the current flows, the voltage across the cell terminals will not be E, it will be E minus IR. It will be E minus IR. My dear, join in. Even if you are late, it's okay. You can always watch the replay of whatever you have missed. Now just imagine, for that same circuit, what I do, I have that internal resistance, but the load is not there. The load is basically a wire, which means you have shorted the cell. Shorting anything means you are connecting the 2 points with a wire. That is the meaning of shorting. In such a case, what do you think will happen? What do you think will happen? If you again end up measuring the current just like before, this capital R is only not there. So you will see that the current will be E divided by R. E divided by R. But there is a problem. Usually what happens is, this resistance is very, very small. usually this is very, very small, because of which what will happen? The current will become high. Because of which what will happen? When the current is high, it will discharge the cell. It will discharge the cell very fast. It will discharge the cell very fast. So if I take this battery and if I take a wire and just connect it across this, that's it. It's gone within couple of seconds and minutes. It will be discharged because a very large current will flow. Many charges will be supplied. Chemical energy will get utilized very quickly and it will get discharged. That's the reason for it. Is that cool, everyone? Understood? That is what they have also explained in these paragraphs, if you notice. So first they talk about how V is E minus IR, and then usually the resistance, if it is small, then you will see very large current will flow. This is that maximum current scenario. This is basically large current or basically maximum current scenario when there is nothing in the way, no load in the way. But that usually should not happen because it can damage the cell. It will discharge the cell really quick. I hope this is clear. So all these three things you should know. Open circuit, this is connected to a load, and finally this is without a load, basically shorting a circuit. These three things they have mentioned over here very clearly. Now usually in NEET exam also and even in NCERT there could be some questions like this, where imagine this is basically your current, this is basically your voltage across the cell, and we know the voltage across the cell V is equal to E minus IR. Now compare this with Y is equal to C plus mx, C plus mx. So clearly you will see who is what. X is your x-axis, which is current, slope is your R, and constant is basically your E, and your y-axis is nothing but your voltage. This is what it is. So if I use this analogy over here, y-axis is voltage, so this should be a straight line. The y-intercept is positive. The y-intercept is positive, which is E. So this is basically your plus E. The slope is negative R. The slope is negative R. So it should go down like this. It will hit over here. It will hit over here. So it will be a straight line when you draw voltage across current. Like this. Voltage across the cell versus the current. If you ask me, what do these points represent? This point is when the x-axis coordinate is 0. That means current is 0. That means it is open circuit. If you ask me what is this point representing, this is when the y coordinate is 0. That means the voltage is 0. Voltage is 0. That means what? There is voltage is 0. That means there is no potential difference across the cell. It has been shorted. It has been shorted. It has been shorted, and that is the reason why you are seeing maximum current. This maximum current was E by R, if you remember correctly. This was shorted. Where is it? Yes, shorted. Yes, E by R. Because there will be no voltage difference here, right? It's a wire. There is no voltage across a wire. That's the reason for it. So this graph is very important. Yeah. Clear? Understood how we brought in that analogy, how we compared it with the straight line equation? I hope it is being added in your notes as we speak, or maybe even after the lecture. Shall we move ahead? Everybody clear till this point? Give me a thumbs up quickly or fire in the chat box. Okay. And if you have forgotten to like the video, quickly like the video. If you have forgotten to subscribe to the channel, quickly subscribe to the Vedantu NEET English channel for your Captain Shreyas Sir. Okay. Now, they talk about cells in series and cells in parallel. I'll tell you, they have done a lot of nonsense, but at the end of the day, the result is very, very simple to remember. So let's not get into the complexity. Let's remember very straightforward, simple things. So when you have cells in series, meaning one cell is there like this, another cell is there like this, and there could be many such cells with some internal resistance. Let's say this is E1 R1, E2 R2, this is En Rn. I can convert it into one single cell in series and one single resistance in series. Okay, I can convert it into one single cell in series and one single internal resistance in series. So what is that conversion formula? It's very simple. Because the resistors are one after the other in series, this particular Rs becomes just R1 plus R2, like that. You just add the internal resistance. Whereas for the total EMF, you just add the individual EMF. That's all. So E1 plus E2, like that, till EM. Let me give you a simple example for this. Imagine this is 3 volts, this is 2 volts, this is 5 volts, this is 1 ohm, this is 3 ohms, this is 2 ohms. If I convert it into one single cell with internal resistance, what will be those values? Think about it. This value will be, all these cells are in series one after the other. So 3 plus 2 plus 5, which is 5 plus 5, which is 10 volts. This would be 1 plus 3 plus 2, which is basically 6 ohms. Similarly, if there is one battery like this, 3 volts, 2 ohms, then there is another battery like this, 5 volts, and then 1 ohm, and then there is another battery like this of 4 volts, and let's say this is 2 ohms. What would be the equivalent battery and internal resistance? Come on, let's see if you guys can figure this out for the next one. Can you figure it out for the next one? Think carefully and give me the answer. The equivalent EMF and the equivalent internal resistance. What is the answer? Let's see. Come on, my dear students. I want to see who is listening, who is understanding. Hi, Tanuja. Welcome aboard. Okay. 14. What is it, Sukanya? Resistance is simple. 2, 1 and 2. So it will be just 2 ohms plus 1 plus 2, which is nothing but 5 ohms. But EMF, 3 minus 5 plus 4. 3 minus 5 is minus 2 plus 4 is basically 2 volts. So 2 volts is the answer with 5 ohms. Many of you just added 3 plus 5 plus 4. You thought it was 12, but that is not the answer. Be careful, because if you look at it carefully, this battery is in the opposite direction. So you need to be little careful and see how they are connected. If you make a mistake in that, you will get a completely different answer. You might be wondering, sir, you made minus sign here, this battery was opposite. Why did you not make the resistance as -1? Because resistance, no matter whether you connect it like this or like this or like this or like that, doesn't matter. It will be the same resistance. But battery, if you connect it like this or like that, it will go from low to high or high to low. So that is the reason why sign will matter for the cell, but it won't matter for the resistance. That is a catch. Yep, many of you made that mistake. Now I hope you understood and you will not make that mistake in the actual examination. Just like this was cells in series, we also have basically cells in parallel. We also have cells in parallel, meaning This is E1, this is R1, this is En, this is Rn. I convert it into one single cell with one single internal resistance, Okay. In this case, the formula for resistance is very simple actually. It is simply the parallel resistors formula which I have learnt in 12th standard, 1 by R1 plus 1 by R2, and you get basically 1 by Rn. The 10th standard formula. Normal formula. The problem is only for the parallel EMF. So EP will be equal to, observe this carefully, you have to write E1 by R1, E2 by R2 like that till En by Rn in the numerator, but in the denominator just 1 by R1, 1 by R2 and till 1 by Rn. That is the only difference. Okay, the only complex formula is for parallel EMF. Otherwise, this is simple. Even this is simple. Okay, there was nothing different or difficult. So let me show you an example so that you get an idea of it. Imagine you had something like this and you want to convert it into one battery. You want to convert it into basically one single battery with one single EMF, a resistance also. You can clearly see they are in side by side mode, that means they are in parallel. So let's try to find 1 by Rp first. It will be 1 by R1 plus 1 by R2. So LCM is 6. So it will be 3 plus 2, which is 5 by 6. So Rp will be basically 6 by 5 ohms. So we got this. All right. What about EMF? Let's try to do that also. It will be E1 is basically 4, R1 is basically 2, plus E2 is basically 6, R2 is basically 3, upon 1 by R1 plus 1 by R2. That's it. That's the formula. So I have shown you how to apply it. Now this will go 2 times, this will also go 2 times. 2 plus 2 is 4, divided by this is 3 plus 2 divided by 6. So 4 multiplied by 6 divided by 5. So this will be 24 divided by 5 volts. 24 divided by 5 volts. Yeah, correct. Understood? Clear how to do these kind of problems whenever you have to find equivalent EMF either in parallel or in series. Great. So that is what it is. So we are now coming to Kirchhoff's rules after finding equivalent EMF. All right. So let me show you some more examples so that you are, properly getting that confidence. Let me show you one simple example right over here of cells and everything. There is a graph given. This is voltage, this is current, and that graph looks something like this. This is 5 volts. This is, let's say, 20. Sorry, this is basically 0.2 ampere. The question is find the EMF and internal resistance of the cell. This is voltage across the cell. This is the current through the battery. Current through the cell. Come on. Let's see if you guys can figure this bit out. Let's see if you can figure this out. It's not difficult. This graph is something which I had given to you. I'm pretty sure you will be able to do it. EMF and internal resistance. Just remember, just some time back I had shown you this particular graph. Where did I show it to you? Right over here. This graph. Yes. This point is E. This point is I max, which is E by R. And this was related to Y is equal to mx plus C. That's it. So there we go. This is like E minus IR is equal to V. Perfect. So this point is basically the y-intercept, which is basically 5. So EMF is basically 5 volts. That part is done. EMF is 5 volt. This point over here, this is basically I max, which is E divided by small r. The maximum current is 0.2. EMF is basically 5. So basically R is 5 divided by 0.2. 0.2 is nothing but 1 by 5 itself. So that means the internal resistance will be 25 ohms. 25 ohms. Understood? Shall we move ahead? Next question. Very good. Excellent. Imagine another example where there is 4 volts, 1 ohm here, and let's say we have something like this, 2 volts, 2 ohms over here, and let's say it is connected to a battery, to a resistor of 2 ohms. The question is, can you find out how much current goes through this particular circuit? What is this value of the current in this particular circuit? When you look at this question, you might get confused, sir. It's a complex circuit, 2 batteries, but don't worry, these 2 batteries are in parallel. So what can I do? I can convert it into a single battery. So the first step for this problem, I will be converting this into a simple circuit. Instead of the 2 batteries, I will write 1 battery. Okay, instead of the 2 batteries in parallel, I will write 1 battery with 1 simple internal resistance, and this will stay as it is. This is 2 ohms. Can I find this? Definitely. Why not? So 1 by Rp will be 1 by R1 plus 1 by R2. So this will be 1 plus 1 by 2, which is 3 by 2. So Rp will be basically 2 by 3. Okay. So this is 2 by 3 ohms. What about this EMF in parallel? E1 by R1 plus E2 by R2. 1 by R1, 1 by R2, 1 by R1, 1 by R2. What is E1? E1 is 4. What is R1? It is basically 1. What is E2? It is basically 2. What is R2? It is basically 2. If you do this, you will get wrong answer. Reason is, check the direction of the cell. So actually speaking, this should be minus. Look at it. This battery is facing this way. This battery is facing this way. So this battery is opposing this battery. So yes, this should be -2. Don't put minus below. So such kind of questions, the minus sign only comes in the numerator, not in the denominator. Is that clear, everyone? Is that clear, everyone? Understood? Pakka? All right. So now you can solve this. So this would be 4 minus 1, which is basically 3. 1 plus 1 by 2 is basically 3 by 2. 3 cancels, 2 goes on the top. So this will become 2 volts. So this is now 2 volts. Now finding the current is a cakewalk. This current will be the voltage divided by the total resistance, which is 2 plus 2 by 3. 2 cancels. So 1 by 1 plus 1 by 3, which is 1 by 1 plus 1 by 3 is 4 by 3. So therefore it will be 3 by 4 amperes. The current is 3 by 4 amperes or 0.75 amperes. Cool. Now you will be able to solve these questions on parallel cells and series cells. It's not that difficult if you see. Okay, I'm showing you examples on how to apply these particular concepts, because oftentimes people go through this theory blobs for by hearting what is this equation. It is so confusing. And you know the worst part, NCERT gave this only for 2 cells, how it will look. But I have given you the formula for even 1000 cells. This will work even for 1000 cells. Okay, infinite number of cells also. Cool. Okay. Now let's come to the next main topic, which is basically Kirchhoff's voltage laws and current laws. See, what happens is many times a circuit may not be series nor parallel. Like, is it possible, sir? It is not series also, not parallel also? Yes, it is possible. I'll show it to you. And in such circuits, you can't simplify it easily. So, there has to be some way to solve such problems. So, that is why Kirchhoff derived a way, and that is basically Kirchhoff's current law and Kirchhoff's voltage law. And they have basically explained it over here, okay, in a very complex manner. But I'll just highlight the important rules over here. First is called as the junction rule. At any junction, the sum of the currents entering the junction is equal to the one leaving the junction. Okay. And okay. Next is basically the loop rule. The algebraic sum of the changes of the voltage around it in the resistors and the cells is basically 0. This rule is obvious. Wow, very good. Excellent. And then the first example only they give is of a cube. You know, such an example actually came in JEE. And even in JEE, they don't ask such questions immediately. But NCERT had that guts. I mean, literally, hats off to them for giving the first solved example after Kirchhoff's law as the cube problem. They don't even give such questions so easily. So anyways, we'll come to the cube problem. But first, let's understand what Kirchhoff's law is. Imagine there is a road like this. I say 2 cars go here. I say 3 cars go in here. Nothing else is happening in this entire situation. After some time, what will happen? These cars are bound to come out. This is all one way. If it goes like this, it can't come back. This is also one way. So they will have to come out in this way. So totally 5 cars will come out of this. Same thing is also applicable even for wires at a junction. This was the junction of a road. Imagine this was 2 amperes. This was 3 amperes. You will 100% see 5 amperes coming out. This is basically called as the Kirchhoff's current law, or basically your junction law or junction law. What is this based on? It is based on the principle of conservation of charges. Conservation of charges. Yes. The total charge has to be conserved. Whatever comes in has to go out. It can't accumulate, nor can it be generated anywhere. If it comes in, it has to go out. That is your Kirchhoff's current law. So in general, I can then say, if I have many branches like this, so many places it will come in, go out, come in, maybe go out, whatever, many things are there. So the total sum of the currents at a junction or basically a node is 0. This is what it is. This is the junction or the node. So whatever you see, the total current at the junction or the node will be 0. Or a better way of writing it is the total currents going in will be the total currents coming out. This is usually the more preferred way of writing it. Okay, so that is your Kirchhoff's current law. Is this point absolutely clear, everyone? Yep. So let's see a simple example on this. Let's see a question on this maybe. This is the question. You have to find if all these currents and directions are given in all these branches, what is the current over here? Okay, let's see who can do it really quick and give me the answer the quickest. You not only have to type fast but also correctly. Don't make any mistakes while doing this. Come on. Yes, Malati, it will be done next. Moving charges magnetism. Thank you, Krishna, Warrior Pandu. Thank you, VS Vetri. Very good, Atluru. We'll come to his loop rule also. Yep. Let's see how many of you can do this question really quick. Come on. Think, think, think. This 5 is going in, 1 is coming out. So naturally the remaining out of it, 5 is coming in, out is 1. So the remaining 4 amperes should go here. It should go here also. Here 2 is going here. 3 is coming out. That means from this more 1 ampere should feed in. So 1 plus 2 will combine as 3. 2 is going out, 3 is going out. So what should come over here will be basically 5 amperes. So 5 amperes should go out here. If 5 is going here, 4 is coming in. So naturally from here, more 1 ampere should go inside this junction. 4 plus 1 will combine as 5 amperes. Next, 1 ampere is going here, 1 ampere is going here. Where will it come from? Obviously this 2 amperes. Okay. So 2 amperes is going here, 4 amperes is going here. Naturally, what is going here is nothing but 6 amperes. So 6 amperes is the answer. Got it, everyone? How to do this question? This kind of question can come in your NEET or even in your board exam. Okay, very simple application of Kirchhoff's current law. Yes, Madhumati, it is 6 amperes. So that was your Kirchhoff's current law, and they decided to explain it in a very, I don't know, random manner. Now let's go to Kirchhoff's voltage law. Let's go to Kirchhoff's voltage law, which is also called as the loop law. This is based on the principle of conservation of energy, basically. Conservation of energy, basically. Now understand this. Imagine there is some mountain, some river, some valley, some plateau, some city, some mountain, some peak, some waterfall, something is there. So you reach here to the mountain, go down inside the valley, go to the plateau, okay, and then you again go to the mountain, come down, you go on the plains, go to the sea, and you again come back to the same point. Let's say you had some potential energy here, gravitational potential energy. Here the gravitational potential increases, decreases, increases, decreases, increases, decreases, increases, decreases, decreases, increases, like that. Finally, what will happen? The total change in your potential energy, what will it be, guys? Won't it be 0? Yep, energy has to be conserved, potential energy will be conserved. You come back to the same place, so you will be at the same gravitational potential energy. Now imagine this was an electrical circuit. In an electrical circuit, is there gravitational potential energy? No, there is electrical energy, electrical potential energy. So if your charge goes around that circuit and comes back, it might increase its voltage, decrease its voltage. Eventually what will happen? The total potential energy change will be 0. That means the total potential drop across a loop will be 0. So that is what it means. So it says that the total voltage drop across a loop when you come back to the same point will be a big fat 0 because of conservation of energy. As simple as that. Now, when you are traveling in a circuit, you might encounter a battery. You might even encounter a resistor. So let's say if somebody is going from here to here, somebody is basically traveling from here to here. When that person travels from here to here, he will encounter a voltage change. He is going from positive terminal to the negative terminal. positive terminal to the negative terminal. So is the voltage drop positive or negative? Obviously it is negative. The voltage has dropped, so the voltage change is negative. So when you go from here to here, then the change in the voltage will be minus E. If somebody goes from here to here, it will be minus E. While traveling in the circuit, somebody goes from here to here, you are going from minus to plus, low to high, obviously the voltage change will be plus E. Obviously the voltage change will be plus E. Whereas over here in the resistor, I will need the direction of the current, and current always goes from high potential to the low potential inside a resistor. Which means if somebody decided to go from here to here, against the current, the voltage change will be plus IR, Ohm's law. Voltage is IR, so it will be plus IR. But if somebody decided to go from here to here, it will be minus IR. What will it be? Minus IR. I hope this is absolutely very clear. Everybody with me on this? Excellent. This is the sign convention which you should remember, and I will now explain through example how to use Kirchhoff's voltage law. Observe carefully. Let me take some random third class complex circuit. This is some circuit. Do you see a loop in this? Do you see a loop in this? Let's say this is E1, this is E2, this is E3, this is E4, this is E5, this is R1, let's say this is R2, let's say this is R3, let's say this is R4, let's say this is R5, let's say this is R6. Let's show some currents also. Maybe the current is like this. Assume the currents. Maybe it is here. Okay. Maybe here it is like this. Maybe here it is like this. Maybe here it is like this. Here actually I don't need the current because there is no resistor. The value is not needed. Maybe here it is like this. Maybe here it is like this. Maybe here it is like this. These are some assumed currents. You can always assume. If it is wrong, if the answer is negative, what will it mean? I have assumed the wrong direction, but magnitude is fine. That's okay. So let's try to apply Kirchhoff's voltage law. Let's start from here. Don't forget, we'll go like this, 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 and come back. Every time I encounter a device, I will either have a positive change or a negative change. But when I add all the voltages, I should get the total sum as 0. So RHS will always be 0. So how will the equation look like? Observe carefully. First, as I go across the battery, from here to here, I am jumping from high positive to low, which is negative. So shouldn't it be negative E1? Everybody gets it? E1 will be negative. I am going like this. Now I go through the resistor 1 in the direction of the current. In the direction of the current, the change is negative IR. So shouldn't it be minus I1 R1 minus I1 R1, the next device? Okay. Then I go over here, I encounter the next device. but I'm going against the direction of the current. When I go against the direction of the current in the resistor, it is always plus IR. So hence the next term over here should be plus I to R2, plus I to R2. I reach here, I go across this battery, negative to positive, low to high. It's a jump. So again, it should be plus E2, plus E2. I reach here, I see I'm going through this resistor, but I'm going against the direction of the current. So when I go against the direction of the current in a resistor, it is plus. So plus I6 R6. I reach here. I go in this battery. I'm going from positive to negative. High, positive, low, negative. I'm going down. So hence it should be basically minus E3. I continue. I reach this resistor. I'm going in the direction of the current, and in the direction of the current it is always a drop, so that's why it should be basically minus I3 R3. I reach here, I reach negative, go to positive, negative to positive, it's a jump high, so it will be plus E4, plus E4. But as I go like this, I'm going against the direction of the current. Against means positive, so plus I4 R4. I reach here, high to low. I'm going down, so again minus E5. I reach here. I go like this. This is in the direction of the current, so it should be a jump down. So minus I5 R5. Minus I5 R5. This whole answer should be a big fat 0. Got it, everyone? This is probably one of the best examples to explain you the signs and how to write Kirchhoff's voltage law. You can't possibly have any confusion after this regarding the signs and the values. Absolutely clear? By the way, can you tell me what will change in this equation? Instead of going like this, somebody goes like this. What will change in the equation? Can somebody tell me? Come on, my dear students, my dear lions. This whole equation, only one thing will change. If I go like this, all the signs will get exchanged. Minus will become plus, plus will become minus. So as an exercise, as an homework for your additional practice, do the same question in the reverse way. You should get the same answer, but wherever there is a minus, there will be a plus. Wherever there is a plus, there will be a minus. That's it. That's the only change. So that will clear your doubt. Exactly. Only the signs will change. Very good, Sukanya. Now, let's solve this cube problem. And also then they have given this particular problem before going to Wheatstone's bridge. So what is this cube problem basically? They have told that you have connected a battery of some volts, 10 volts, resistance network which is like a cube. Each resistance being 1 ohm, determine the equivalent resistance of the network and the current along each edge of the cube. Okay. Actually, are you able to visualize this circuit where a battery is supplying current, it enters one corner, it goes in this cube in different paths, finally comes out of this corner which is diagonally opposite, and we have to convert this cube into one single resistor. Into one single resistor. How do I do it? Okay, let's see. All right. First of all, I feel we should see how the currents will get distributed. And I feel in this particular question, the currents will get distributed in a symmetric way. Why? Because cube is a symmetric figure. So if you carefully think of a cube, you will realize that there is a beautiful line of symmetry like this, or you can think, if I go from this diagonal to this diagonal, once I enter from here, I can see that there are three different paths like this, and like this. Three different paths which are basically symmetrical. Whether I go like that, like this, or like this, they are symmetrical. Do you see that? Everyone? Same way, if I think of the line of symmetry, if I think of that line of symmetry to be this one, the current enters from here. Can you see it will get divided like this, as well as like this? Symmetry will be involved. So same current will go here, same current will go here, same current will go here. How much current was entering in? Let's say it was I. What will happen? Is you will see I by 3, and I by 3 current getting distributed. Agree or disagree? Yes, Sridhar will be moving to moving charges and magnetism after that. Equally, 3 parts. If there were 4 branches, 4. I by 4, I by 4, I by 4, I by 4. Okay. Also, with the same logic, at this particular junction, the same current should come out, and it will come from 3 different ways. It's a cube, it's a symmetrical diagram. So naturally, from here, and from here, I by 3, and I by 3 current will come in. 3 I by 3's currents will accumulate here and come out. I am trying to find the distribution of currents using symmetry of a cube, because that will help me solve the problem. Without currents, I can't apply Kirchhoff's laws, I can't do anything. That's the reason for that. Okay. Now, after going here, can you see there are 2 equivalent ways? So one, it can go like this or like this. So I by 3 gets divided into half each. So what is half of I by 3? 1 by 3 into 1 by 2 is 1 by 6. So each one of them will be I by 6 and I by 6. Same thing here. When this current reaches here, there are 2 paths. So hence, this will be also I by 6. This will be also I by 6. After reaching here, there are 2 paths. One here, one there. So naturally, you will see this as well as this. Each will be I by 6 and I by 6. That's the distribution of the currents. I have covered each and every side. Now you're like, okay, sir, you did all this. So what nonsense now? What will you do? I'll say I will apply Kirchhoff's voltage law across the loop. You can choose any loop that you want. I will choose a simple loop. I'll go like this maybe. Let's go like this. Simple circuit will go. Let's go like this. Okay, I have highlighted it for you for simplicity. That's all. Now, in this particular loop, let's figure out what are the currents. First, in this cell, I current will go. That same current I will go. Here, how much current will go on this side? This side, I by 3 is there. This side, I by 6 is there like this. And on this side, again, I by 3 is there. And then again, it comes back to I over here. Please remember, this is actually a resistor. Over here, this is actually a resistor. Even this over here is a resistor. Even this over here is a resistor. Don't forget that each resistance is 1 ohm each. Okay, so I'll just call it as R, R and R for now. R and R. Let's apply Kirchhoff's voltage law and see what do we exactly get. Come on. Let's start from here. Starting here, I reach negative, go to positive. So there is a jump. So plus E. So negative to positive, jump. Go like this, nothing here, reach here. Go across the resistor in the current's direction. So I will drop how much? Current, which is I by 3 into resistance. I reach here. After that, I go in the direction of the current. Current is basically I by 6, resistance is R. In the direction, it will be dropping, so negative. I reach here. In the direction of the current, it drops. So it is I by 3 into resistance. There is nothing here. And I come back to that same point. So hence, this should be 0. Hence, this should be 0. Take all these gentlemen on the other side. So I'll have IR 1 by 3 plus 1 by 6 plus 1 by 3. LCM, of course, is 6. LCM, of course, is 6. So this will be 2 plus 1 plus 2. So what's happening next? So therefore, E will be equal to IR. 2 plus 1, 3. 3 plus 2 is of course 5. So that's what I will get. Now I'll be like, okay, sir, fine, you got this. What will you do with this? What will you do with this? Just imagine, instead of this complex circuit, what you had was just this battery and just one single resistance, which I call it as the equivalent resistance. How much or how will the current, voltage and resistance be related as? Obviously, it will be related like this. E will be equal to I into R equivalent. E will be equal to I into R equivalent if there was one resistance. So doesn't this equation resemble that? Isn't this resembling this? So that means this entire cube is behaving like 5R by 6. 5R by 6. Got it? Everyone? So hence the equivalent resistance is 5R by 6. Since our original resistance was 1 ohm, so if R is 1, 5 by 6 ohms is the answer. That is what they have done, but in some fancy manner. Where is it? 5 by 6 R. Okay? I hope this is clear. And if you ask me how much current will go, the current will be nothing but substitute this. Voltage is known, you will get the current also. That's not difficult. Loved this question. Hi Mahadev. Thank you Diksha ma'am for the blue hearts. Thank you for awakening the kids. Thank you so much. Finally. Yes. Thank you so much Mardel. Thank you Jasmine. Thank you so much guys. So beautiful question about cubes. This has been asked in JEE. If it is asked in NEET, don't be surprised because it is a direct NCERT question. Some of you kids might want to remember this value. I'm perfectly fine with that. No harm. But main thing what you learn from this question is how to apply Kirchhoff's laws and how in a complex circuit you can solve it without series parallel knowledge. You can solve it to find equivalent resistance. You just had to assume some battery supplying current. You find the distribution, take some loop, write the Kirchhoff's law equation. You see voltage is some current into some resistance. That thing becomes the equivalent. The process of finding equivalent is what you should understand. If you by heart this, I am perfectly fine. But at the same time, understand what we were doing at the background. Okay, we are trying a method for any circuit to find equivalent by connecting this battery, assuming the supplies, distributions, and then voltage is current into resistance. Voltage is current into resistance. That's the main aim. Alright, Warrior Pandus, crystal clear, all Luru, very good Krishna, very good Mahadev plan. Awesome Sukanya, awesome Mahadev, awesome Malati. Perfecto. So where do we go now? Awesome. Here we come to the next NCERT example. Determine the current in each branch of the network. Now, see, over here, many batteries, blah, blah, blah are there. But already, they have shown some distributions. Let's see how this works. So there is a battery, resistor, 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 battery over here. So just assuming few currents right over here like this. Just check this out. Some current I1 they have assumed over here. This current will go here. Some of it will go here. Some of it goes here. How much will go here? Think about it. If some of it goes here, how much will go here? The remaining I1 has come in, I2 is going out. So naturally this will be I1 minus I2. Which law did you use here? Subconsciously, Kirchhoff's current law. Currents coming in, currents going out must be the same. Currents coming in, currents going out must be obviously the same. Okay. Now, after reaching here, okay, they have assumed some current in this particular branch, which they call it as I3. See, I1 minus I2 enters here. I1 minus I2 enters here. I3 goes out. So what should happen over here? Okay, if they assume this to be like this. If they assume this to be like this. If I assume this to be X, X enters in, I1 minus I2 also enters in. Collectively, it becomes I3. So therefore, X will become how much? I3 minus I1 plus I2. So I minus I1 is there, I2 plus I3 is also there. I2 plus I3 minus I1. So that is exactly what they have written down over here. Till this point, everything clear? How these values they have got? This was I2 plus I3 minus I1. Okay. Then over here, what they have done, whatever current goes here will obviously also go over here. So this is I3, this is I2. I3 and I2 together, what will that become? That will just become I2 plus I3. Both of them together, Kirchhoff's current law, it will become I2 plus I3. So once this is done, you can apply Kirchhoff's voltage law multiple times to solve the problem. But in the NEET exam, you will never get such a complex question because it is very time consuming. But I will just show this to you, how Kirchhoff's law can be applied. You can choose any loop that you want. Okay, for example, they have chosen some loop ADCA, I think ADCA. Okay, so I'll just show you how it works and then we'll choose any random loop and see how it works. ADCA. This loop, if you choose starting from here, how will the Kirchhoff's law equation look like? Starting from here, going in the direction of the current, it will obviously drop the voltage. So minus I1 minus I2 into resistance, which is 4. Reach here, going against the current, so it should be an increase. Current into resistance. So I2 plus I3 minus I1 into the resistance, which is 2. Reach here, go in the direction of the current, so negative IR. So I1 into 1 is equal to 0. That's how you write Kirchhoff's voltage equation. Clear, everyone? You can choose even more loops if you want. You can choose even more loops. Say for example, somebody chooses this particular loop. Okay, you start from here, go like this, and come back over here. How will that Kirchhoff law equation look like? Kirchhoff's voltage law. Start from here, go like this. I encounter a battery, negative to positive, so I'm jumping by 5 volts. Negative to positive, low to high, it's a jump up. Reach here, go in the direction of the current, that means there is a drop. Current into resistance. So I2 plus I3 into 2. In the direction of the resistance, drop, so minus. Current is this one. So I2 plus I3 minus I1. Resistance is basically 2. This is equal to 0. Got it, guys, how to apply Kirchhoff's law? If you understand how to write it, that's it. Yeah. So they have just written down the equations and solved it, and you get the answers. That is not the point over here. Main thing is, are you able to apply Kirchhoff's law or not? So even let's see if you can write it down for some another equation, another loop. Maybe you go like this. Maybe you go like this, starting from point A. So if you start from point A and apply Kirchhoff's voltage law, I'm going in the direction of the current. So negative I2 into resistance. In the direction of the current, negative. So this current into resistance. So I2 plus I3 into 2. In the direction of the current, so again negative, and that is basically I1 into R1. And there is a battery over here, negative to positive. So negative to positive, so plus 10 is equal to 0. Okay, plus 10 is equal to 0. I hope this is clear. I think I missed that 10 over here by mistake. My bad. So I think while going like this, I missed that 10 over here. So my bad. So plus 10 was also there. I just saw that over here. So plus 10. Yep. Great. Done. Sorted. Cool, guys. Everyone? Yeah. So this is how you write Kirchhoff's law equation. Okay. So now we are coming to the last part of this, which is basically the Wheatstone's bridge. Is an application of Kirchhoff's law as shown in the circuit. And they say if you have resistors, etc., then that is called as a Wheatstone's bridge. There is a galvanometer, and in the case of a balanced bridge, in general, there will be currents flowing across all the resistors as well as the current through the galvanometer. The special case, this is very important, special interest is the case of balanced bridge. When the resistors are such that the current through the galvanometer is 0, such is called as the balanced condition. Balanced condition. So all of this they tell, and we obtain the balance condition to be this is called as the balance condition, where the galvanometer will give 0 or null deflection in the circuit. Wheatstone's bridge will provide a practical method to determine unknown resistance. Yes, determination of unknown resistance. This is basically called as a meter bridge. Okay, and then they give that particular example over here. Okay, let's understand what this is. Listen to me carefully. Imagine there is a resistor here, there is a resistor here, like this, and then there is a resistor here, and there is a resistor here, like this. Say for example, some current entered over here, okay, it got divided into two branches like this. So if for example at this point the voltage was 20 volts, after reaching here the voltage became, let's say, 12 volts, then maybe it became over here back to 0 volts. Maybe while passing here the current became, let's say, 10 volts, and here it became 0 volts again, obviously. Now tell me, if by chance I connect some device which deflects if current passes through it. Galvanometer is such a device where you pass the current, it gets deflected. If I connect a galvanometer, will it deflect or not deflect in this scenario? Tell me that. Thank you, Divya. I'm so glad, and I really hope all the students in the country, especially learning in English medium, find this channel. That's the reason why I ask you to like, share, not just physically through, on your WhatsApp, but also talk about this in your school, amongst your friends, amongst your relatives. What do you think? Will it show any deflection or not? Well, there is clearly a voltage difference which is there. So definitely current will flow from high to low voltage. So current will flow and this current won't be 0. So there will be deflection. There will be deflection in that galvanometer. This setup of those resistors is called as a Wheatstone. Wheatstone is the name of the person. It's not like, sir, there was a stone made of wheat and he made a bridge. Somebody told me this and I hit my head. Imagine some teacher had told one student, and that student came and asked me, sir, there was really a bridge, sir. In that bridge was made of stones, and you know that stone was made of wheat. Then I realized teacher was not at fault. The teacher was joking. The student did not understand the joke. Because the student had asked, why is it called Wheatstone's bridge? So teacher funnily said, stones were made of wheat and then they made the bridge, and then it was unbalanced. So the bridge fell down. Like London Bridge is falling down. Okay. So this is unbalanced because there is deflection. Versus a scenario where you have these resistors like this. Again, let's say this is 20 volts, maybe this is 15 volts, maybe this is 15 volts, this is 0 volts. Somebody now decides to connect a device which deflects when passing current. There is no voltage difference, so clearly the current through this will be 0. So there is null means 0, null or no deflection. Such a condition for that Wheatstone is said to be balanced. So this is called as a balanced Wheatstone bridge. This is called as the balanced Wheatstone bridge. Exactly. Very true, Sukanya. Such a student is intelligent, sir. You know, that's how I understand whether the student is smart or no. When I crack a joke, if the student laughs, then I understand the student is intelligent, smart, will do well. Student doesn't laugh, I only get tense. Why student didn't laugh? He didn't understand my joke only. I was joking to him. Okay. And this balanced Wheatstone bridge, happens if this is R1, this is R2, this is R3, this is R4. This by this and this by this are equal. When R1 by R2 is R3 by R4. That's when it is balanced. If it is not equal, it will be unbalanced. This is the balancing condition. Is this absolutely clear, my dear warriors? Yep. By the way, you know what? This is even valid for even more resistors like this. Even more branches can be there, guys. This is 1 ohm, 2 ohms, 3 ohms, 2 ohms, 4 ohms, 6 ohms, 2 ohms, 4 ohms, 0.5 ohms, 1 ohm, 1.5 ohms, 10 ohms, 20 ohms, 30 ohms. Oops. Some crazy circuit. Somebody was really jobless while making this circuit. Imagine in this circuit, they ask you to simplify. You'll be like, sir, what is this? But let me tell you, this is actually simple. Yes, this is actually simple. You know what? This is a Wheatstone's bridge, but this is multi-layer, multiple Wheatstone's bridge are there, or extended Wheatstone's bridge. If you see, there are how many branches? 1, 2, 3, 4. Each branch has three resistors. These resistors are in the ratio 1:2:3. This is 1 time, this is 2 times, this is 3 times of this. 0.5 into 2, 0.5 into 3. 10 into 2, 10 into 3. 1:2:3 ratio. So the ratio is same. Ratio is same. That's it. All these yellow resistors are useless because it is a balanced bridge. So useless because there will be no current in the circuit. So you can just forget them. So this is the equivalent circuit. Just draw it without that. Now these are in series, these are in series, this is in series, this is in series, and they are in parallel. So now you got it, guys, how the circuit is actually a simple circuit. Everyone, so this is an extended Wheatstone's bridge which is still valid. The ratio of the resistors in all the branches must be the same, then it works. 1:2:3. Okay. So there is a question. Oh, by the way, before going there, now they tell that, listen, you can use Wheatstone in some way to find an unknown resistance. Kind of makes sense actually. Imagine this is like when I show a resistor with an arrow mark, what does it mean? What does it mean when I show a resistor with an arrow mark? It's a vector quantity, is it? No. It means I can change the resistance. So this is like a fixed resistance, but this means it's a variable resistance. This X happens to be an unknown resistance. This happens to be a variable resistance. These are like fixed, these are like some fixed resistances. So what happens is you basically vary this resistance till there is no deflection here. When there is no deflection, basically balanced condition, what will happen is that R by X will be R1 by R2, rather X will be R into R2 by R1. You know R2, you know R1, this R you changed till you adjust and see there is no deflection. That's it. You can find the unknown resistance. So this Wheatstone is used to find an unknown resistance using some fixed known resistance as standard resistances. Got it, my dear students, how this works? Okay, that is what they have mentioned in the last few things. Determination of unknown resistance, that setup is called as the meter bridge setup. Okay, so there are 4 arms of a Wheatstone's bridge as follows. Oh, by the way, some of you will be like, sir, these experiments which are there, no sir, please can you teach me that? How many of you know the magic? How many of you know the magic? The magical words. Experimental physics. Let me type it. Ooh, what is this? Wow, experimental physics. It was the first time somebody did it on YouTube, especially on the English channel. Click on this. It's one single class, complete physics, all experiments explained one by one. It's the same me. I might look a little younger. Yeah, the age difference between me then and now might be around 90 to 95 years, not much. Okay, so I hope you won't find it too old. So just go through this, all experiments, guys. All experiments are there right over here. Every single thing explained in detail. So check this out. Okay, some of you do not know this. That's why I had to show this to you. Okay, cool. So what is this? AB is 100, BC is 10, CD is 60, DA is DA. Why DA? CD is basically 5, DA is 60. The 4 arms are shown. Galvanometer of 15 ohm resistance is connected across. Just calculate the current through the galvanometer when a potential difference of 10 volts is maintained. And then they start doing all this and they find the current. Now, you might be wondering, sir, why did they do this? Isn't this balanced? Shouldn't the answer be 0? Just check it out. What is the ratio? 100. This is 100 divided by 10, R1 by R2. This is 60 divided by 5. This is basically 10:1. This is basically 12:1. So they are not equal. So hence it is unbalanced circuit. Oh my God, you'll be like, sir, unbalanced, sir, what to do now? Meter bridge. Shreya, please check that experimental physics class. Okay, you will find it there. Now, whether it is deleted or not, we'll have to see, wait and watch for the syllabus to be officially released. So, till that time, okay, just assume that only that basic concept is there as per NCERT, but otherwise it is not there. We don't know. It might come, it might not come. We have to wait for the official brochure to come. So, till that time, no comments. Okay, some people will make videos on guessing. This is there, that is there. NTA declared 2 exams are there. NTA declared 5 exams are there. NTA is doing this. Some people, news articles, rumor, they say that it is official NTA news. I don't know how people see that videos. Forget people saying, how teachers can make such videos. I never understood that. It's really, really shameful for such teachers to make such videos. So make sure that you are not stupid enough to fall for such, clickbaits. Okay. So in such a scenario, my dear students, what you should remember is that current will flow. So you have no other choice but to use Kirchhoff's current law and Kirchhoff's voltage law. No other way. Okay. Atiluru, the scholarship test syllabus I have already mentioned over here. How to prepare for MVSAT strategy revealed. In this particular video, right, I have given the complete syllabus for all the grades, 11th, 12th, everything. So check this video out. I given the pattern, everything, the syllabus, everything. So just check it out. Okay, this video is there in the live tab of our channel only. Preparation strategy. So for solving this question, you assume the distribution of currents. There is no other way to solve this particular question. Like, say for example, current I will pass over here. This will get distributed as I1 and maybe I2. Okay, and once this I1 reaches here, some current will go through the galvanometer. So if I1 is reaching here, IG is going here. So the remaining will be I1 minus IG. I1 went here, IG went here. So remaining will be I1 minus IG. And this IG will come here. This I2 will come here, will add up to become I2 plus IG. Finally, they will all add up to become I back again, and it will go through this battery. You just have to choose some loops and solve the question. You can choose any loops. Say for example, I choose this particular loop, or I choose this particular loop. Choose these loops and solve using Kirchhoff's voltage law. So if I apply Kirchhoff's voltage law over here, say starting from this point, I encounter a battery, so plus E, which is basically plus 10. Across the resistor in the direction of the current, so minus I into resistance, which is basically 60. Current into resistance, so in the direction of the current I am going, so minus I2 plus IG into 5. Back to the same point, so this should be 0. So this is one equation. This is one equation. Similarly, you can write an equation for this also using Kirchhoff's voltage law again. So let's say you start from here. In the direction of the current, it is a drop. So I into resistance. In the direction of the current, it's a drop, so minus Ig into 15. Opposite, it's always a rise, so plus I2 into basically 60. That is equal to 0. So make equations, solve them. That's what they have done. If you notice, they have exactly done this. They have written an equation, another equation, solve this to get the answer. Is that clear? So that was the method to do it. No other way, no shortcut, nothing else. Cool. This is how you solve unbalanced Wheatstone's problem. Okay. So that completes this chapter of current electricity, my dear students. I hope you have understood this chapter conceptually. You are able to see how we have applied it in problems. And now, once this series gains momentum, and if you show that support by liking, commenting, and subscribing, we will start with problem solving, which is the most important thing. We have to scale up our level till the final NEET examination, guys. So make sure you are doing all those efforts, subscribing, liking, commenting, because we need to start very soon with problem solving too. Okay, so let's get up, guys. Next chapter coming up, chapter number 4. Not many chapters are there. Within no time, within a month or two, you will see all the NCERT 12th standard chapters will be done. Okay, you will be prepared for your boards as well as for NEET examination. Simultaneously, our RNA series is continuing, where we are doing all the concepts of NEET with PYQs and the theory as well. Okay, take care. Have a great time. Bye bye. Captain Shreyas signing off. Hasta la vista.